Hey guys, so this is going to be the Exam 2 review video. So the Exam 2 will take place on Wednesday the 17th. So this is just to briefly cover everything that you need to know for the exam, starting with Chapter 4. Then we'll look into Chapter 5 and 6. And then Chapter 7, which we went over on today, the 15th, will be most of it will be on the exam, not Hess's Law. So chemical equations, definitely need to know how to balance them, no doubt. Balance all different types. You may or may not see one of these really tough ones on there. Since we did do 2 examples, it is fair game. So I'll tell you that. There are some the combustion ones. Sometimes you might end up with a decimal, maybe 5/2, 10/, or 11/2, something like that on the oxygen, on the O2, in the reactant side, and you would have to multiply the entire equation by 2. And there's some other ones you can practice. Limiting reagent, know how to figure out the limiting reagent. Theoretical yield, percent yield. Know the difference between theoretical yield and actual yield and how you calculate those. So if you say for an actual yield you got 337, knowing a chemical equation, figure out the theoretical and then divide the 2 and you get the percent yield. Stuff like that. And oxidation reduction, so to know how to spot a redox reaction by assigning the oxidation numbers, the oxidation states, to different elements using these rules in the table. Oxygen is always -2, except for when it's in a peroxide, but you're probably not going to see peroxides. And then know how, if I give you any compound, you should be able to determine the oxidation states of every atom in the compound. For chemical equations, you should be able to assign oxidation states to every atom in the equation and then tell me which one is reduced and which one's oxidized. Also, which one is the reducing agent, which one's the oxidizing agent, and also know oil rig, so what oxidation and reduction means. Meaning oxidation is losing electrons, reduction is gaining electrons. So that's very important to know. And know that one can't happen without the other. They both happen together. This is more of the same thing. And that's it. That's it for Chapter 4. So now going on to Chapter 5, we learn about solutions. So know what a polar molecule is. Know the difference in the method of dissolution of ionic compounds when compared to non-electrolytes. So ionic compounds, you either have strong or weak electrolytes. But for things that are non-electrolytes, like sugars and usually larger compounds, you'll see this kind of water attacking the solute and not breaking it down. So it won't break down into its ionic components because there are no ionic components. When you break down into ionic components, you end up with different charges, and electrons can flow freely through the solution, creating a current, which is creating an electrolytic solution, otherwise creating electrolytes. So that's important to understand that concept. Acids and bases, understand what an acid and what a base does. So acids have hydrogen and release hydrogen ions into the solution, whether it be water or whatever, such as this equation. Those are for strong electrolytes, strong acids, and weak electrolytes. The weak acids is one type of them. And know that if you have 100,000 molecules, you can expect only one of them to dissociate. So a very small percentage will dissociate. So then you can have insoluble and soluble and even partially soluble ionic compounds. And some of, like silver, whenever you see silver, always have a red flag. Silver, lead, and mercury are going to be your 3 elements that are going to raise red flags for you. So if you know these solubility rules, you should be good. And basically what this means, not even all of them, it's just really the first 3. If you know the first 3, you're good. Because, well, all of them to be safe. But if you were in a crunch, the first 3 are really good. And then just know silver, mercury, and lead usually are not soluble. Unless they're with these 3. Unless we're with acetate or nitrate. Because acetates and nitrates are always soluble, even if they're with silver. So that leads us into strong acids and weak acids and strong bases, all this stuff. This is good. Remember, Hickel, Hibber, High, Hino, and Clo-So. It's a very good acronym to understand and know how you could just memorize all of your strong acids very easily. Strong bases are group 1A, 2A hydroxides. So those lists are important to know. Precipitation reactions are important to understand, and also you will be seeing them on the exam. So it's important to know what they are, how they work. So you have two ionic compounds which are both initially soluble. They get added together to their anions or cations switch, however you want to look at it, and you have a solid that forms. This solid is a solid precipitate. So it'll be solid and it will not be broken up in solution. Meanwhile, you have other ions that are remaining that we call spectator ions, which will be remaining in the solution, just floating around as plus and minus. So understand how to write the complete ionic equation, and then to cancel out the spectator ions to write your net ionic equation. These are both important things to do when we're dealing with precipitation reactions. This list is just the same thing reiterated about the solubility rules. Just know them to the best of your ability. Here's more precipitation reactions. Acid-base, strong acid, strong base. Titrations, know the definition of a titration. Know that from the homework, I think you had a couple problems on this, where you calculate the concentration of acid or even concentration of base required to neutralize a known amount of the other one. So if you know that 100 milliliters of 1.5 molar NaOH was used to neutralize 200 milliliters of an unknown volume, or an unknown concentration of acid, you could first find the moles of base that it was added, then do the chemical equation. If it's a 1-to-1 ratio, you just say, oh, the same moles of base that was added is the moles of acid that was neutralized. And then you can do that math and then figure out the concentration. So redox again, we talked about that. Molarity, very important to know. The equation will be given on the exam. So know how to do molarity, moles over liters. Know how to do dilutions as well. M1V1 equals M2V2. And that is it from chapter 5. So now chapter 6. So chapter 6 involves gases. So know your kinetic molecular theory of gases. Understand the units for pressure. Know the units for all the different gas laws. So not necessarily memorizing the gas laws, just knowing the different units that are acceptable in each one. So Boyle's law, Charles's law, Avogadro's, Gay-Lussac's, which is not written here, also the combined gas law. As long as temperatures in Kelvin, it doesn't matter what the other ones are, as long as the ones are the same as the twos. For the ideal gas law, it does matter because we have our ideal gas constant, R equals 0.08206. Liter ATM, it should be per Kelvin mole. Not liter ATM Kelvin mole, liter ATM per Kelvin mole. And the pressures in ATM, temperatures in Kelvin, N is the number of moles all the time. So here's a good summary of the list of laws. Again, they will be given, and understand really what they mean, and like in Boyle's law, for example, the amount of gas is held constant and the temperature is held constant. The only thing that's changing is when the volume expands, the gases have more room to move and their pressure decreases. So stuff like that. Charles's law, same thing. Know the concepts. Avogadro's law concept, kind of like filling a tire. If you fill up the tire, the volume will expand. All right. Also, I mean, if you keep the volume fixed, which car tires, the volume's kind of fixed, the pressure will increase. That's why you need to know your tire pressure. Ideal gas law, units for gas law. Molecular speed and velocity. So know as you get smaller gases, they tend to move faster. Their kinetic energy is constant, but their speed, their average velocity is increased. But their average kinetic energy is the same for all gases because it's some relationship to their size and their molecular and their speed. So if you have a small molecule that moves fast, it will have the same kinetic energy as a large molecule that moves slow. The root mean square velocity, it will be given on the exam if needed. I don't think you might have one problem on it. So yeah, this equation it will be given. So know that in this case, R is going to be our 8.314 joules per mole Kelvin. Temperature is always Kelvin. Na is going to be Avogadro's number. Na equals, yeah, it is, right? I think it is. That equation's stupid. Where's the real equation? There it is, this one. So 3R is going to be our 3.1 or 8.314, and then is going to be your molar mass in kilograms. So this equation is the best for root mean square velocity. Then you have effusion. So don't really worry about diffusion. Effusion, you have this inverse relationship of the rates, or inverse rate ratio, if you will. So your rate 1 over rate 2 equals the square root of the molar mass of 2 over the molar mass of 1. So understanding that ratio and how you can possibly figure out ratios or which one's faster. So if I gave you a question between oxygen gas and hydrogen gas, which one has a higher rate? Or for every 10 molecules of hydrogen gas, how many oxygen gases will go through? So the answer is, all right, we got to find the relationships between the rates. This is a ratio, so you can figure out if you call hydrogen A and oxygen B, you can do the math and figure that out, figure out their relationship to each other, and let's say it's times 5 difference, or I think it's actually a times 4 difference. Then you would say, all right, 4 times the amount of H2s would go through for every O2. So molar volume, standard conditions is STP, know that, and 22.4 liters. It's our key number. So any 1 mole sample of a ideal gas has a volume of 22.4 liters. And you could use that in different equations to figure out the molar density. Don't really worry about molar density. Partial pressures, it's good to know. You just add them up. The mole fraction, we talked about this is more towards the end, the pressure fraction, meaning the partial pressure of A over the total, is the same fraction as the mole fraction. That's how ideal gas works. That's how ideal gases work. And you can use the mole fraction to figure out the partial pressure just by multiplying that percentage by the total pressure. That's kind of going backwards to what you already know. So you can do that example, and then deviations from the ideal gas law, you get to real gas. Don't really worry about real gases, and that's it. And then chapter 7 is what we learned today. So I'll pull up this thing, chapter 7 study guide. All right, so here we have potential energy. Know the differences in the energy types. Know exo and endothermic. Know that nothing ever gets colder because objects lose heat or energy to objects with less energy. So things just transfer heat. There's no really hot or cold. State functions. Know that it doesn't matter the path. Sorry, I'm exhausted. It doesn't matter the path to get to the top. Non-state functions are going to be heat and work. State functions are going to be energy and enthalpy. So I'll put that here. Energy and enthalpy are your main state functions. Meanwhile, heat and work are not. And then you have equations. You have delta E equals Q plus W. Here's an example. Specific heat, you're going to have Q equals, don't use this one. Don't worry about this one at all. Do this one. The Q equals MCAT. That's important. So that'll help you for every specific heat problem. Know that your temperature change is in either Celsius or Kelvin. I know it says Celsius here, but the temperature difference is no different between Celsius and Kelvin. Your constant is going to be joules per gram Celsius. To be Celsius, like it says here. And this is, I think we did this equation during class. This question, I mean. So enthalpy, so know that enthalpy is basically the heat and energy in 1 mole. So all the energy, not 1 mole, sorry, the energy in 1 chemical reaction. So either exothermic or endothermic. So the energy gained or lost in a chemical reaction is the enthalpy. So enthalpy does have, don't worry about the enthalpy equation of E plus PV. Don't worry about that. Also, this one's important too. The pressure with work and volume. So your work equals negative P delta V. And you can actually plug that into your gas equations. So you have equations that relate P and V. Let's say if I gave you a question where I told you to determine P from some gas problem and then using that P find the work using this equation. So that could be fair game. Or to find the energy using the work and then I give you heat separately. So you calculate the work, you would convert it to joules using this conversion we did today, 101.3, and then you would add the heat to that. And then enthalpy, don't worry about the Hess's law because that will be on the exam 3. Yeah. Okay, so that's it. That's about it. Good luck, and if you have any questions, let me know. I'll be making the exam tomorrow probably, so you can bribe me, and I'll try to make it easy. No, I'm just kidding. I won't bribe you, or you won't bribe me. But yeah, it'll. You guys have been good, so I won't make it too bad. I'll try to have mercy. All right, so that's it. Have a good night, and I will talk to you guys on Wednesday.